Okay. I think Mike should be fine because same as thing. Yeah. Alright. I am going to be doing lessons 11 to 20 today. So the first one is time delta. More reading. Okay. Gotta move the mic closer too, I guess. Okay. Time delta. We've seen how we can use our character's process function to make it move continuously. Func process delta rotate. Yeah, okay. But it's not just our character that has a process function. Almost everything in the game has a process function. Dozens of times per second, Godot runs every process function in the game to update the game world. After that, it displays an image of the game world on the screen. We call that image a frame. Godot then moves on to calculate the next frame. As this happens dozens of times per second, you get the illusion of movement. This is similar to how traditional animation works. This sounds like frames per second. You may have heard of frames per second, or FPS for short. Games often run at 60 frames per second. It means that everything in the game updates 60 times each second. The number varies while playing, depending on the game and the device it runs on. On powerful computers, you may get frame rates in the hundreds or thousands of frames per second. Let's look at the process function in more detail. What parameter does the process function take? Func process delta rotate. So it takes delta. The process function has one parameter named delta. Frames take varying amount of time to calculate. Depending on the game, the computer, and what the game engine needs to calculate, frames take more or less time to display. There will always be milliseconds variation from frame to frame. This is why the process function receives a delta parameter. The delta represents a time difference. It's the time passed since the previous frame in seconds. We can use it to ensure that the changes between frames don't make the game's behavior unreliable. This is because different computers run differently, so a fast computer will have more frames per second than a slow computer. If we ignore delta, the game experience will vary. Depending on the computer, delta helps make the game experience consistent for everyone. What do we know about delta? It's this one, right? It's the time it took Godot to complete the previous one. No, it's not. It varies each frame. It's value in seconds. Oh, it's all of them. Okay. Alright, I did not pay attention. It's okay. Delta is the time it took Godot to complete the previous frame in seconds. It's very small because frames happen many times in a second. It varies each frame because Godot needs to process more or less each frame. Multiplying by delta. The delta you get in process is the time difference in seconds. It will generally be a tiny decimal number. To apply delta, you need to multiply your speed values by it. Okay. Got it. When multiplying by delta, you make motion time dependent rather than frame dependent. That's essentially to make your game consistent and fair. Why do we use the number 3.0 in this example? At the top of the lesson, we made the robot rotate a fixed amount of every frame, 0.5 radians. In the example below, we now multiply the argument by the very small delta value, a value way below 1.0. It makes the robot turn at a constant speed over time. However, multiplying by a number below 1.0 like delta makes the result smaller. To compensate for that and make the robot turn fast enough, we use a large number than before, 3.0 instead of 0.05. Those numbers have two different units. 0.05 is an angle in radians, while 3.0 is an angular speed in radians per second. When you multiply a speed by time delta, it gives you an angle. Don't worry if it's a little confusing for now, it'll eventually click as you deal with speed, acceleration, and motion in your game projects. Water break. Why the time between frames matters. The time it takes to display a new frame varies. If you don't take that time into account in your code, your game will have gameplay issues and bugs. Godot provides that time to the process function through the delta parameter. In the example below, the top robot moves using delta. As a result, it moves at a fixed speed. The bottom robot moves over a constant distance every frame without taking delta into account. It will move faster or slower than the top robot on your computer. The bottom robot will move differently for everyone. Oh. Okay, cool. Multiplying time-sensitive values by delta makes them time-dependent rather than frame-dependent. Thanks to that, we get reliable movement over time. Without delta, frame times vary from computer to computer and during gameplay. Because of that, the movement will differ for every player, making the game inconsistent and messy. So what does this mean? Rotation speed times delta. So we are multiplying rotation speed by delta. In the next practice, we'll use delta to make rotating time dependent. So at the moment, the rotation of the robot is frame dependent. Rotate 2. Add delta to make the rotation speed time dependent. The robot should rotate 2 radians per second. 2 radians per second? Is time dependent? Does that mean it's 2 is delta like that? Is that right? I hope it's right. Nice. I passed. Okay. I was not paying attention to the lesson. Okay, but now I know. Alright. In this practice, make the robot move in a smooth circle using delta. To get this movement, the robot should rotate 2 radians per second and move 100 pixels per second clockwise. Please write the values in the parentheses when calling the function. If you define extra variables, we will not be able to check your practice. Okay, so there are 2 functions I can use here. Let's see. To get this movement, a robot should rotate 2 radians per second and move per second clockwise. So it's rotate 2 times delta. I need the spaces, it bothers me a bit. And then the other function is move local, I can't spell, local x, then 100. I think that's what it's asking. Oh. Two radians per second and move 100 per. Oh. Okay. Well, I'm doing something wrong. It's moving in a circle. Oh, I didn't move it by delta. Alright, I'm back. Right. and move 100 pixels per second. So what I didn't do was this one. I forgot to do this part. Alright, it's good now. Next, lesson number 12. This looks really tiny, but using variables to make code easier to read. In this lesson, we'll make our code easier to follow and understand at a glance. Take a look at this example. Func process delta rotate 4 times delta. In the above example, what does the number 4 mean? It's how fast the character rotates. Okay. The code above rotates the character 4 radians per second. We can guess what a number represents by looking at the function names, but it's hard to recall what this number does by quickly looking at the code. We've seen how different functions have their own names. Using these names communicates to developers what the function do. So rotate 2, move local x 100, and then move local y negative 200. As we learned in lesson 8, we can also assign labels to numbers to help us remember what they do. We called these labels variables. A variable is a label for a value we can save, change, and read later. Let's recap how to define a variable. Var space variable name space equals space value. We improved the first example to make this clear what number 4 does. So var angular speed 4. This variable is defined outside of the function, and then func process delta rotate angular speed times delta. Labeling a value makes the code easier for us to read now and in the future. In the example above, which line defines the angular speed variable? This one. Var angular speed equals 4. Nice. If we define variables outside of a function, we can reuse them in different functions. Because any function can use variables we define outside of them, we call these variables script-wide. Here we use the angular speed script-wide variable in both the process function and the set angular speed function. So var angular speed equals 4. This variable is defined outside of the function. Func process delta rotate angular speed times delta. Okay, and then func set angular speed new angular speed equals to angular speed equals new angular. Okay, so it's a new function that sets the new angular speed pretty much. We can also define variables inside of functions. We align the variable assignment by indenting to make it part of the function body. Make sure to create the variable before using it. If we define a variable inside of a function, only that function can use it. Func process delta var angular speed equals 4 rotate angular speed times delta. Then func set angular speed new angular speed. And then this doesn't work because this was called inside of this function and it doesn't know what to refer to here pretty much. The angular speed variable only exists inside process because we defined it there. The set angular speed function can't use it. Trying to use it there will result in an error. Here's what the error might look like. The identifier angular speed isn't declared in the current scope at line 6. So this was not defined. Why this happens that set angular speed function can't use the angular speed variable because it isn't script-wide. It also isn't the set angular speed function. How to fix this? Make sure you define the angular speed variable in the set angular speed function or define it outside the function so it's script-wide. Where can we define variables? Outside functions and inside functions. You're right, functions can use any variable defined outside of functions. These variables are script-wide. If we define a variable inside of a function, only that function can use it. Variables are also great at grouping values that control how a character behaves. Grouping them in this way allows us to easily change them. And the variables to control movement. So var horizontal speed is 200, var jump strength is 150, and var gravity is 90. The variables for combat: health 40, health maximum 80, attack power 10, defense 4. In the following practices, we'll define variables and use them with some familiar functions to make your code more readable. Okay, let's give the 4 here a label so we know what it does. Create a variable called angular speed outside of the process function. So I need to do, oh, there. So, oh my gosh, I can't type. Variable angular speed equal, oh, there's nothing. Okay, and then replace the 4 with angular speed. Wait, give the 4 here a label so we, oh, the speed is 4. Okay, got it. Is what it's asking me to do. Nice. Okay, there's something wrong with the code here. Can you see what it is? Run the code and read the error. Correct the code so it works as intended. Should I still run it? Okay. Alright. Func process delta var angular speed equals 4, rotate that. Okay, so this isn't called. So technically I just put this one outside the function, but I'm gonna run it. So it says right here at line 6, this doesn't work because this one needs to be taken out. There. It should be like that. Continue. Alright, conditions. In the previous lessons, we decreased and increased a character's health, but there was no limit to how much health they could have. So func take damage amount is health minus equal amount, health heal amount, health plus equal amount. So as a result, the player could increase their health indefinitely, which we do not want. Boop. So healthy. What happens to health when we damage our character? Suppose our character has 100 health. What would the value of health be if we called take damage 5 times? It would technically be negative 25 because it doesn't have anything to catch it. We can use a condition to run selectively. Conditions make your code branch into 2 paths. If the condition is met, the computer will run the corresponding instructions. Otherwise, those instructions will not run at all. Video games and other game programs are full of conditions. For example, game input largely relies on conditions. If the player presses the button on a gamepad, the character jumps. Jump. Boop. Okay. When the computer checks a condition, this is called to evaluate a condition. All conditions evaluate to either true or false. Either the player is pressing the button or not. Either the character is touching an enemy or not. In our case, if the health goes over a maximum value, we want to reset it to the maximum. To define a condition, we use the if keyword. We write a line starting with if. Type the condition to evaluate and end the line with a colon. So func heal amount, health plus equal amount. If health is greater than 100, then health is equal to 100. Notice the comparison sign. We read the symbol as greater than. We've seen how function definitions use a colon at the end of the first line and nest content inside. In GDScript, this syntax is a recurring pattern for all code blocks. The computer knows which instruction belongs to the condition because they are indented. Okay, so this one, currently the health is 75. So if I press the heal 50, that means it'll plus 50, but technically it goes to 125. Since it's over 100, it stops at 100. Nice. Comparison. In the above example, we use the syntax greater than syntax to mean greater than. We can compare numbers in other ways too. Greater than means greater than, less than means less than, equal means equal to, and exclamation mark equals means not equal to. Here's how we might use these in if statements. So if health is greater than 100, then pass. If health is less than 50, then pass. If health is equal to 25, pass. If health is not equal to 7, pass. The pass keyword prevents errors in our code when a line cannot be empty. For example, we must have a line of code after a function definition or if block. When you don't know what to write yet, you can use the pass keyword as a placeholder, and Godot won't give any errors. In the previous example, if there was nothing below the if lines, Godot would give an expected an indent block after if error. Which of these statements are true? So 2 is less than 3, 1 is not equal to 3, 3 is greater than 1, and that's it. You're right. The comparison 3 is greater than 1 means 3 is greater than 1, which is true. The comparison 2 is less than 3 means 2 is less than 3, which is true. The comparison 1 is not equal to 3 means 1 is not equal to 3, which is true. The comparison 2 is equal to 1 means 2 is equal to 1, which is false. The comparison 3 is less than 1 means 3 is less than 1, which is false. Or else, the if keyword comes with a complementary else keyword. If you write an example block, if you write an else block after an if block like so, func run var speed equal 120. If speed is less than 100, print your slow, else print your fast. So this would technically be your fast. Ta-da! The else block will run whenever the condition above isn't met. In the following practices, we'll use conditions that improve the way our character health changes so it has limits. If this series of if statements is all wrong, change the comparison so each comparison matches the instruction below. Keep the value and statements as they are, only change the comparison signs. As a reminder, the comparison signs are greater than, less than, equal to, not equal to. The line health greater than 5 means the line health less than 5 means health is less than 5 because health is equal to 100 there. This is false, so print health is greater than 5 won't run. Okay, I am having trouble reading right now. Okay, so function run var health equals to 100 if health is greater than 5, so I need to do greater than 5. If 1 is less than health, if health is equal to health, and if health is not equal to 7. Alright, run. Nice, done. We have a heal function that adds an amount to the character's health. Add to the function so the character's health is never greater than 80. Okay, so func heal amount health plus equal to amount. So if health is greater than 80, then health is equal to 80. Run. Preventing health from going below 0. When the robot takes damage, its health can be negative. We might want to display the health number on the screen like in Japanese RPGs. We don't want negative numbers. We want to stop at 0 instead. Calling the function should reduce health by amount. If health goes below 0, set it to 0 again. So take damage, health is minus equal amount, and then if health is less than 0, then health is equal to 0. Nice. Multiplying. Our robot's health is always between 0 and 100, but as our robot fights, we want to increase its strength and toughness. When a character levels up, it might deal more damage to enemies, gain new abilities, or in our case, gain more health. We define a level variable to keep track of the level of the robot. It starts at level 1. When the robot has defeated enough enemies, we call the level up function to increment the robot's level. So var level equals 1, function level up is level plus equals 1. As we briefly saw in the last lesson, our robot could have a range of variables that can increase when it levels up. So var health equals to 100, var max health equals 100, var power equals to 5, and var defense equals to 2. In this lesson, we'll focus on increasing the robot's max health. The variable max health is the maximum amount of the robot's health can be. We can change our heal function to use this variable. So variable health equals to 100, variable max health equals to 100, func heal amount is the usual, so health plus equals to amount. If health is greater than max health, then health equals to max health, which makes sense because you want to cap at max health. We could add 5 to the max health every time the robot levels up. So func level up level plus equals to 1, max health plus equals to 5. This would increase the max health the same amount every time. If we graph max health, it'll look something like this. It'll just go up. Yeah. This growth is linear. In our case, we want a feeling of more and more power as the robot levels up. We want to graph like this. Oh, that's exponential. This growth is exponential. With each level, more max health is added than the previous level. To get the exponential growth, we multiply the max health by an amount greater than 1 each time the robot levels up. To multiply values together, we use asterisk. What is the value of damage? So var level equals to 5, var power equals to 3, func calculate damage is var damage equals to power times level, so it's 15. Boop. We multiply the power by level using asterisk to get the result of 15. We can use asterisk equal in the same way as minus equal and plus equal. What is the value of damage now? What do you usually say when you see these? Do you go like minus equal? Minus equal? Like the more I read it, the more it feels like I'm saying it wrong for some reason.
Say minus equal.
Okay. What is the value of damage now? Var level equals to 5, var power equals to 3, func calculate damage, var damage equals to power times level, and then damage times equals to 2. So power times level is 15 times 2 is 30. Submit. Nice. So the value of damage starts at 15, then damage times 2 multiplies it by 2 to get 30. Let's level up our robot and add exponential growth to max health. Var level equals to 1, var max health equals to 100. So func level up, level is plus equals to 1, and max health is times equals to 1.1. In the practice, you'll increase the robot's max health and add a specialty ability to our robot to make it extra tough at high levels. Okay. Let's make the robot stronger when it levels up. Add to the level up function so it does the following. Increases level by 1, increases max health by 10%. Okay, so level is plus equals to 1, and then max health is times equals to 1.1. I want to run it again. I want to see it from thing. I didn't even look at the thing on the right. Cool. Looking very cool. My robot gained help. When your robot's level is 3 or more, we want it to take a lot less damage. Add to the take damage function so the following happens. If the robot level is greater than 2, reduce the damage amount by 50%. The robot is level 3. An enemy is going to attack for 10 damage. This damage should reduce to 5. Okay, so function take damage amount. So pretty much if level is greater than 2, then amount is times equals to 0.5, and then like that, pretty much it looks like that. So this is inside here, so if the level is greater than 2, then that means the amount of the damage is going to be halved. And then it applies the health amount, and then if health is less than 0, then health is thing. So right now, if it takes a 10 damage, if an attack goes for 10, it goes through here. Since it's level 3, then it takes 5 damage, which is health is 100 minus 5. Okay, should be good. Nice. Continue. Lesson complete. Ooh, vectors. 2D vectors. Suppose we want to increase the size of the robot when it levels up. As you may recall, we do this by using the following code. Scale. So function level up, scale x plus equals to 0.2, and scale y plus equals to 0.2. Okay. As we talk about in lesson 7, the scale variable has two subvariables to it, x and y. This is because the scale is a vector 2, which stands for two-dimensional vector. A vector 2 represents 2D coordinates. Oh, okay. What are vectors? A vector in physics is a quantity with a magnitude and a direction. For example, a force applied to some object, the velocity, speed, and direction of a character, and so on. We often represent this quantity with an arrow. In Godot, 2D vectors are a common value type named vector 2. Unlike plain numbers, they store two decimal numbers, one for the x-coordinate and one for the y-coordinate. Boop, boop, boop. Osu spinning time. Okay. So far, you've come across two variables in the course, which are vectors. Which are they? Vectors. Position and scale. Oh, thanks. Okay. You're right. Both scale and position have x and y subvariables. So Godot uses a vector 2 to store their values. Vectors are great for games. Vectors are essential in a video game. They allow you to represent a character's movement and speed and direction, calculate the distance to a target, and more. With little code like this, 𝖙𝖒𝖊𝖉𝖎𝖆𝖘. Oh, it's so cute. You've probably seen games where enemies move like this. This is done with just 7 lines of pure vector calculation code. The code is a bit too difficult for now, so we'll spare you the details. But this tutorial gives you a glimpse of what 2D vectors can do for you and your game projects. This is so cute. It's moving. Okay, we scale the robot again, this time by adding to it directly using a vector 2. The following code has the same effect as the previous example. So func level up, scale plus equals to vector 2 to, wait, there's no close bracket? Maybe not. I don't know. Okay. Notice how we use a parentheses in 2 arguments inside parentheses, just like other functions. We call this a constructor function call. You can think of it as a special kind of function that creates a particular type of value. The code vector 2, 0.2, comma 0.2 constructs a new vector 2 value with its x set to 0.2 and y set to 0.2 respectively, using vectors to change the position. We can add and subtract vectors to positions because of its vector. If we wanted to move our robot to a new relative position, we would add a vector 2 to its position. So that one is position plus equals to vector 2 to 22. So it moves x by 20 and 2 y. So 2 down. So it goes a little that way. Huh. This is more. Oh, maybe it's 20. Just gets cut off here. I don't know. How would you move the robot 50 pixels to the left? So 50 pixels to the left means. So it would be this function or this one, because this one is just the position minus equals to vector 2, which is x and y, and to the left it's x. 50, well, minus 50 because it's minus over there, and the reason why I don't pick the point, the one with the dot x, is because that breaks the vector 2 part. Yeah. So you're right. Position minus equals to vector 2, 50, 0 subtracts 50 to the subvariable x and 0 to y. Position dot x minus equal to vector 2, 50, comma 0 tries to subtract a 2D vector to the subvariable x, which is a decimal number. The value types are incompatible. If you try to do this, you will get an error. In the next few practices, you'll use vectors to change scales and position values. Okay. Add a line of code to the level up function to increase the scale of the robot by vector 0.2, 0.2 every time it levels up. So at level up, it goes, increases the scale of the robot. So scale plus equals to vector 2, 0.2, 0.2. I think it's like that. Run. Nice. Continue. The robot's level has, oh my gosh, this robot is huge. Has increased a lot and so has its size. Let's fix this to resetting the robot scale and position values. Create a function named resetRobot that sets the scale and position of the robot. So reset robot, and then scale. Okay, so the x and y subvariables of the robot scale needs to be 1. The robot's position needs to be 0, 0, as in the previous practice. Make sure the vectors when dealing with, okay. Make sure to use vectors when dealing with scale and position. So scale equals to, what are the functions again? Oh, okay, I don't remember the functions. Okay, let me try to remember. Scale. It's just like that. Scale equals to vector 2, and then it feels like something's off, but I don't know. Position equals to vector 2, 0, 0. Because I'm just setting it at 0, but like, what determines this? But yeah, maybe there's just other code that I don't see. Because like there's probably like a different function somewhere that actually does the displaying of the scale. Yeah, should be fine. Anyways, introduction to while loops. You've seen that you can use functions to reuse code. In this lesson, you'll learn about loops. Loops help you repeat code. To illustrate how loops work, let's take a game board split into a grid. Our robot can move to neighboring cells by changing a vector variable named cell. It represents the current cell the robot is in. When we increase cell.x, the robot moves to the right. Note that we delay the robot movement in the app to help you visualize how it moves. The following code will normally move the robot instantly. So for this one, it says function move to the right, cell.x plus equals to 1, so it moves 1 to the right, and then cell x move another plus 1, so another 1 to the right. So cell equals the vector 2, 0 point. Wait. Cell, so it's currently at 0, 1. 0, 1. So it's this one. It's in this one. Because x, y, and usually the first column or row is considered as 0. So it moves one right and then another right. We can move diagonally by adding a vector 2 directly. So that one is cell plus equals to vector 2, 1, 1. So it goes like that and then that. Nice. The above code works for a predefined board with the size of vector 3, 3, but the move to end function wouldn't work if the size of the board was different. The robot would either stop before the end or go too far. To implement a general solution for all board sizes, we can repeat the robot's movement until it gets to the end. For code that repeats, we can use loops. While using while loops to repeat a code, you can use a while loop to make the computer repeat a block of code until you meet a specific condition or decide to break from the loop. Here's how we use a while loop. So var number equals 0, while number is less than 4, print number, so number plus equals to 1. So this only works until 3. So it'll be 0, 1, 2, 3 pretty much. We use a variable number to keep track of how many loops the while loop completes. Each time we go through the while loop, we add 1 to the number. The while loop keeps running for as long as the condition is true. In this case, it keeps running while number is less than 4. You can see the following code is executed 4 times in the console. So function run, pretty much this is right there. So it prints out the 0 first, and then a plus 1, and then plus 1, and then plus 1. So 0, 1, 2, 3. Okay, let's apply this to our move to end function. This time we compare the number of loops with the board's width. We go through the loop until we reach the width of the board. Note that we move the robot until its position is 1 less than the board width because we are counting tiles from 0. A board of 3x3 cell would have cell coordinates going from 0 to 2 on both the x and y axis. So let's see. Function move to the end while cell x is less than board size x minus 1. So cell x is less than board size x, so x is 3 minus 1, so it's 2. So cell plus, okay, with that, and then move to end. Nice. Good job. While loops can cause issues. If you are not careful, your while loop can run infinitely. In that case, the application will freeze. Take a look at this code example. So var number equals to 0, while number is less than 0, draw a square. So because there is nothing increasing number, it'll be stuck drawing more squares. What would happen if the computer tried to run the code above? It would draw squares infinitely until the program is terminated. Submit. You're right, because we don't increment number within the while loop, it always stays at 0. As a result, the number is always lower than 0, so we never break out of the loop. Since there is no way to exit the loop, the computer will attempt to draw squares infinitely, which will freeze the program. When the program stops responding on your computer, it's often due to an infinite loop. When we use while loops at first, you will not need while loops often. Even the code we show here has more efficient alternatives. Also, there is a safer kind of loop, for loops, which we look at in the next lesson. Okay. Yet, while loops have important intermediate to advanced level uses, so you at least need to know that they exist and how to use them. We use while loops every time we need to loop an unknown number of times. For example, games run in a loop that typically generates 60 images per second until the user closes the game. This is possible thanks to while loops. There are other good uses for while loops. Reading and processing a file, like text document line by line, processing a constant stream of data, like someone recording audio with a microphone, reading code and covering it into instructions the computer understands, various intermediate to advanced level algorithms like finding paths around a map for AI. Let's practice some while loops. As they're useful to know, it's also an excellent opportunity to practice 2D vectors. Then we'll move on to the safer for loops for the following lesson. Oh, this is so long. Okay, then yawning. Our robot has decided to stand at the top of the board. Complete the move to the bottom function so the robot moves to the bottom of the board. The board size is determined by vector 2 board size. The robot's current cell is vector 2, 0. So 2, 0. Okay. Make sure to use a while loop so the function works for any board sizes. So while the position. Oh, cell. Okay. While cell dot y is less than board size dot y, because we're just going to the bottom, right? Yeah, board size dot y minus 1, then cell equals to cell plus equals to vector we're removing it one at a time, so cell equals to vector. We're not moving the column, but we're moving the row, and then that's it, right? Then should be it. I think that's it. Okay, let's run it. Oh wait, oh, vector 2. There. Continue. Introductions to for loops. In the last lesson, we looked at while loops. We found they were useful if we don't know how many times we should repeat code. However, they can result in infinite loops. If we're not careful, the loop below never ends because we never increment numbers. So var number equal to 0, while number is less than 3, cell plus equals to vector 2, 1, 1. So it increases that, but the number stays the same, so it's just infinitely. There's a safer and often easier kind of loop, the for loop. We will look at it in this lesson. Unlike while loops, for loops don't run infinitely, so it's much less likely that you'll get bugs in your game. We recommend favoring for loops over while loops because of this. Let's change the code above to use a for loop instead. The loop below will change the cell 3 times. So for a number in range, oh, so this one's like Python. Okay. For a number in range 3, cell plus equals to vector 2, 1, 1. Let's explain what's going on. The range function go.𝑑 has a helper function range. Calling range bracket n creates a list of numbers from 0 to n minus 1. So calling range 3 outputs the list of numbers 0, 1, 2, and range 5 outputs 0, 1, 2, 3, 4. What list of numbers would range 6 create? What would print range 6 print in the console? 0, 1, 2, 3, 4, 5. Alright, you're right. The function range n creates a list of numbers from 0 to n minus 1. The output list will start with 0 and end with 5. So calling range 6 will output a list of 6 numbers which are 0, 1, 2, 3, 4, 5. How for loops work. In a for loop, the computer takes each value inside a list, stores it in a temporary variable, and executes the code in the loop once per value. So func run for number in range 3, print number, so it will be 0, 1, 2. Run. Nice. In the above example, for each item in the list 0, 1, 2, go.𝑑 sets numbers to the item, then execute the code in the for loop. We'll explain arrays more thoroughly in the next lesson, but notice that number is just a temporary variable. You create it when defining the loop, and the loop takes care of changing its value. Also, you can name this variable anything you want. This code behaves the same as previous example. So func run for element in 0, 1, 2, print element 0, 1, 2. Okay, so it prints that. Okay. In both examples, we print the value of the temporary variable we created, number in the first example and element in the second. As go.𝑑 moves through loop, it assigns each value to the array. It assigns each value of the array to that variable. First, it sets the variable to 0, then to 1, and finally 2. We can break down the instruction the loop runs. You can see how a loop is shortcut to code that otherwise gets very long. So func run var array 0, 1, 2, var element, and then element equals to array 0. So that means it takes a 0 and then prints the 1. The element equals array 1, which takes that one and prints 1. The element equals array 2, which is this element, the 2, and then it prints 2. So run 0, 1, 2. We can put whatever code we like in the loops code block, including other function calls like draw a rectangle, using a for loop instead of a while loop. Here's our old move to end function, which used a while loop. Func move to end while cell.x is less than board size minus board size dot x minus 1, cell x plus equals to 1. If we use a for loop instead, the code becomes a little simpler. So function move to end for number in range board size 0.1 minus. Okay, for a number in range board size dot x minus 1, cell dot x plus equals to 1. So rather than constantly checking if the robot reaches the end of the board with the for loop, we take the board's width beforehand, then move the robot at a set amount of times. The function will still work the same. You can execute it below. So it goes like that, then move to the end. In the practices, we'll use a for loop in different ways to get you used to using them. Okay, using a for loop to move to the end of the board. Once again, the robot has decided to stand at the top of the board. This time, use a for loop to move to the bottom. Function to have it. This time, use a for loop in the move to bottom function to have it move to the bottom of the board. The board size is determined by the vector 2 variable board size. The robot's starting cell is vector 2, 0. So for what should I name it? For n, I'm used to n. For n in how is this done again? For n in board size y minus 1, cell plus equals to vector 2, 0, 1. Right? Yeah, it should be like that. Next, use a for loop to remove the duplicate code in the run function. In this practice, we revisit the turtle and drawing rectangles. With our new knowledge of for loops, we can condense this code to make up less space and make it easier to modify. The turtle should draw 3 squares in a horizontal line. The squares should be 100 pixels apart. So instead, I go like for n in range 3, 3. Jump that, draw that. That's it. Nice. Alright, creating arrays. The range function we saw in the previous lesson outputs a list of numbers. For example, calling range 3 produces the list of numbers 0, 1, 2. Func run for numbers in range 3 print number. So it'll print 0, 1, 2. A list of values, numbers or otherwise, has a precise number in code. A precise name in code. We call it an array. So we can say calling the range function produces an array of numbers. We could directly write and use the array inside our for loop instead of range function. You can run the next function step by step to see how it works. So func run for number in 0, 1, 2, print 0, 1, 2. As you see, the code still works the same. Notice that when we create a for loop, we also create a local variable to which the loop assigns one value per iteration. Above, we named it number because the array we loop over contains 3 numbers, 0, 1, and 2. But we can name it anything we'd like. Func run for element in 0, 1, 2, print element. So it prints the same thing. If we unwrap the for loop above, we get the following code with the exact same behavior. So func run var array 0, 1, 2, var element equals array 0 print. Okay, so it's the same thing. It prints 0, 1, 2. The syntax of arrays. We write arrays this way in GDScript. Bracket value 1, comma space, value 2, comma space, etc. You start with an opening square bracket, then you write comma separated values that compose the array. Finally, you need to close the square bracket to complete the array. Here are a couple of valid arrays. Notice how you can mix values and how they don't need to follow one another. So it'll be 1, 2, 6, 7, and then vector, and then random stuff. Because arrays themselves are value type, just like the number of vector 2, we can assign arrays to a variable to re-access them later. That'll come in handy in the next lesson, where we'll use those variables in loops. So var number 1267, var vector, and number, those stuff. Okay, but first let's see when you use an array. When you use an array in computer programming, we use arrays all the time. Precisely, you'll use them whenever you need to store a list of things. You always need lists of things in games. The player's party in an RPG, the items in the player's inventory, the high score in an arcade game, the objects in the game world. All of those and many more rely on arrays. Using an array to follow a path. Let's look at the widespread use of arrays in games. Finding and following a path. In games, you need allies or monsters to find their way to the target, whether it's the player or some point of interest. To achieve that, we use pathfinding algorithms. As the name suggests, those algorithms find the path between 2 points and allow AIs to traverse the game. Water time. Okay, many of those algorithms use array of vector 2 coordinates to represent the path. Take this turtle pet. Take this turtle pet. It wants to follow the robot, but there are rocks in the way. How can we tell it where to walk to reach the robot with an array? Okay, so var path to robot. So vector 2, 1, 0. So it goes here. The vector, it goes here. Then goes here. And then there. And then there. Then there. And then there. Every value in an array is a vector 2 and represents a cell the turtle needs to walk through. Together, all the values in the array represents a path we can draw. In the upcoming lesson, you will see how we can use arrays to store player inventory or design attack combos. For now, let's practice creating arrays. Alright. So, the turtle wants to meet the robot, but it cannot find its own path. Fill the turtle path array with vector 2 coordinates indicating where the turtle should move to avoid the obstacles and arrive safely to the robot. The turtle can move up and down, left or right. It cannot move diagonally. We recommend copying and pasting to fill the array with comma-separated vector 2 values quickly. Okay, so vector 2, but then it'll be like 0. Then I take this, copy, then that, then it goes to 1, 1, that, 2, 1, three, 1, 4, 1, 5, 1, and then 5, 2, and then 5, 3. So it's 1, 0, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 5, 2, and 5, 3. Run. Nice. Continue. Hello, welcome. In this tactical game, the player and computer can select multiple units at once. You need to call the select units function and pass it an array of vector 2 coordinates to know which units to select. Each vector 2 in the array represents a cell with a unit. You can pass arrays and function calls as arguments. As an array is a value type the computer recognizes, you can pass a whole array as a single function argument. Select the units on which the board is passing the correct array. Okay, that whole thing just like went over my head. Okay, in this tactical game, the player and computer can select multiple units at once. You need to call the select unit function and pass it in an array to know which units is selected. Each vector. The unit, you can pass arrays and functions as arguments. Select all units on the board by passing the correct array. So what is it asking? So am I just, do I just put, so this isn't an array, so I think it's just asking me to just list all the locations of where, like, all the thing is, right? That's what it is. So that's the second one is 5-1. Then the third one is 4-2. And then the last one is 0-3. 0-3, right? 1-0, and then 5-1, and then 4-2, and then 0-3. I think that's what it's asking me, right? Is it not? What is it asking? Oh, wait, I'm missing a bracket. Oh my gosh. I can't. Right there. I'm missing this bracket here. There. Is it not? Expected comma or thing. Oh, wait. That's why. There. That's why it wasn't working. There. Alright, next. I don't understand what that practice was for though. I guess it's just getting used to identifying the creating arrays maybe. Okay, so looping over arrays. We use a range function in combination with for loops. So func run for number in range 3 print number. So it'll print 0, 1, 2. Alright. The range function produces an array that the for keyword could loop over. We can give for loops any array, and they will loop over them just the same. Instead of using the range function, we could manually write the numbers and get the same result. For number in 0, 1, 2 print. I swear we're doing this over and over again. For each element inside the array, the for loop extracts it, stores it in the temporary variable named number, and executes the loop's code once. Inside the loop, you can access the number variable, which changes on each iteration. The code works regardless of the array or where you store it. Often you will store arrays and variables for easy access. So var number equals to 0, 1, 2 for number in numbers print number. What will the code print? So var number 0, 1, 2 for numbers in numbers print number. So it'll print this. It'll print 0, 1, and 2. You're right. Compared to the previous examples, we store the array in number variable. Using the numbers variable in our for loop allows the computer to access the array of numbers like before. We have 3 numbers in the array 0, 1, and 2. The loop extracts each of them sequentially and assigns it to the number of temporary variables. As the loop processes each number, the output will print 0, 1, 0, then 1, then 2 each on separate line. Making the turtle walk with the loop. In the previous lesson, you made a turtle walk along a path by writing vector 2 coordinates in an array. So it goes like that. It's a for loop that takes the turtle walk along the path. The loop works like this. For each coordinate in the array, it moves the turtle once to that cell. So func move path for cell in path, turtle dot move to cell. Yeah, that's what I figured that one does. But like this one, I guess. Okay, it's the same principle with the unit selection. For each coordinate in the array name selected units, we check if there is a unit in that cell. If so, we select it. In that case, we use an array, a loop, and a condition together. So var units equals to blank, array var selected units equals to blank array. Func select unit cell. For cell in cells, if cell in units, select unit append cell. So for cells in cells, for cell in cells, if cell in units, append. Okay. Alright. Alright. Water break. Okay. Continue. The code above uses several features you haven't learned yet. In a condition, the in keyword allows you to check if a value exists in an array. The array's append function appends to a new value at the end of the array. Notice the use of a period after the selected units variable to call the append function. It's because this function exists only on arrays. When functions exist only on a specific value type, you write a dot after the value to call the function to it. We'll revisit those two features again in the following lesson. The beauty of loops is that they work regardless of the size of your arrays. The code just works whether you have 1 or 10,000 units to select. It is all accomplished with only a couple lines of code. That's the power of computer programming. In the following practices, you will use arrays combined with for loops to achieve similar results. Practice. Okay, our AI pathfinding algorithm provided a path for the robot to move to the right edge of the grid. Your task is to use a for loop to make the robot move. To move the robot, call its move to function like so. Robot move to. The move to function only exists on the robot, which is why you need to access it this way. Okay. So for, what should I say? For cell in robot path, move to cell. That's what I think it's asking me to do, right? The method move to isn't declared in the current class. Oh, robot.move2. There. So the reason why this one I couldn't just do move2 because move2 is not in this thing. In this program, technically it's in a different program, like another. Like it's not on this one. Yeah, the robot call its move to function like so. Robot move to. Yeah, it only exists in like probably a separate thing called robot. But yeah. Okay, drawing. Wait, back to the drawing board. We want to draw many rectangles, something surprisingly common in games. However, writing this code by hand can get tedious. Instead, you could store the size of your shapes in arrays and use a loop to draw them all in batches. That's what you'll do in this practice. Use a for loop to draw every rectangle in the rectangle size array with the draw rectangle function. The rectangles shouldn't overlap or cross each other. To avoid that, you'll need to call the jump function. So pretty much it is asking me use a for loop to draw every rectangle in the rectangle sizes array. But where is it jumping to? Alright, I don't know where it's gonna jump to, but let's do this. So for rectangle in rectangle sizes. Draw rectangle and then rectangle and then jump. I don't know what jump takes. Jump takes an X and Y. So where's it gonna jump to? Can I just hardcode that? I'll just do like 0, 0, 250. X, I'll just do 250, 250, 0. Draw rectangle. Too few arguments for. Okay, so rectangle dot x and rectangle dot y. There. Continue. Nice. Alright, this is my last lesson for today, and I am doing strings. Okay. So throughout this course, we've mostly stored numbers and variables, but what if we wanted to store a player's name? This is where strings help us. Strings are instrumental in games and applications. We use them to display the information such as the description of a spell or the name of a character. What are strings? A string is a value type which holds text. To create a string, you write the text wrapped in question. For example, this is a text string. The quotation marks differentiate strings from other value types and function names. You may remember we've used strings before the previous lesson. Func run var my name equals to string robot. Print my name, so it prints the string robot. Okay. Under the hood, strings are arrays of characters. In fact, we can use a for loop to loop through the characters of a string, as we would with any other array. So func run for character in robot print character, so it'll be like capital R and then lowercase o-b-o-t, like that. And then which of these are strings? This is a string and this is a string. So you're right, 1 and name are strings. 1 only contains a character and doesn't represent the number 1. Name is made up of 4 different characters. So why we use strings? Every piece of text you see in this app is a string that Godot is displaying for us. Much like how vector2 variables make calculations easier, string variables come with many helper functions and tricks we can use. We can use arrays to store strings too. This is useful for chaining animations. In this example, the play animation plays a specific animation. So var combo jump damage damage jump level. So function perform combo for action in combo play animation. Oh, cool. I never thought of, okay. So a whole combo is like a whole animation thing. And then it runs through that and uses that as a, okay, cool, okay. In the next few practices, we'll use strings in combination with different concepts from earlier lessons. Currently, the robot has a number stored in the robot name variable. Change the robot name variable so it's a string instead. You can give it any name you like. I will give it my name. There. Nice. In this practice, we'll chain together animations using an array of strings. You might find such combinations in fighting games. The robot has the following animation names. Jab, make the robot perform a quick punch. Uppercut, the robot uses a powerful jumping punch. Populate the combo array with animation names as strings. Then for each action in the array, call the play animation function to play them. The array should contain 3 values. So the robot makes 3 attacks, 2 jabs followed by 1 uppercut. Alright, so it's jab, jab, and then uppercut. Like that, right? And then for action in combo, play animation action. Like that. Nice. Continue. Alright. So I have finished lesson 10. Wait, lesson 11. I started lesson 11 today, so I finished lesson 11 to 20. So all I have left is lesson 21 to 27, which is functions that return a value, appending and popping values from arrays, accessing values in arrays, creating dictionaries, looping over dictionaries, value types, specifying types with type hints. I don't know what that last one is, but maybe it's something new I'll learn. But yeah, I will end it here because it's a lot of talking and my throat kind of hurts, but I tried my best. It's like yesterday, it was a good hour-and-a-half stream. But yeah, because I was reading so much, it's just straining on my throat. So I'm kind of looking forward to the end of it tomorrow. But then after that, I will play more games and start making my own game probably. But yeah, thanks for joining my stream. I'm gonna end it here. Good night, goodbye, or good morning if it's morning for you. But yeah, goodbye. Thanks for watching.